We are going to do the 2014 AMC 12B, problem 13. Real numbers a and b are chosen with 1 is less than a is less than b, such that no triangles with positive area have side lengths 1a and b, or 1 over b, 1 over a, and 1. What is the smallest possible value of b? Now when I see no triangles with positive area, I don't have very many theorems and formulas and rules that deal with triangles that don't have positive area. So when I see this, what I think is we should start by looking at triangles with positive area and then reverse what we have so that we can look for when there are no triangles with positive area. So let's look at a triangle that has side lengths 1a and b. Because we know that a and b are both greater than 1, we can draw it like this, where we have 1a and b. And one of the rules when it comes to triangles is the triangle inequality, which says that b is always less than a plus 1 for a triangle with positive area, because we can see that b is the shortest distance between this point and this point because it's a straight line. Whereas if we go through 1 and then a, which is a length of 1 plus a, we're going in a more roundabout way, so it's going to be a greater distance. We also have the second triangle, 1 over b, 1 over a, and 1. Now when we look at that triangle, b is the biggest number, which means that 1 over b is going to be the smallest number. So this triangle is going to have 1 over b down here, and then again a is greater than 1, so 1 over a is going to be less than 1. So this is 1 over a here, and then this is 1. Now with this triangle, the most useful triangle inequality will be that 1 is less than 1 over a plus 1 over b. Again, because 1 is the straight line, so it's going to be the shortest distance. So these are the two inequalities that we have with a and b for triangles with positive area. Since this question is asking about when there are no triangles with positive area, all we need to do is flip these inequality signs so that these inequalities are both false, and therefore these triangles won't be able to exist. So in that case, we have b is greater than or equal to a plus 1, and then we also have 1 is greater than or equal to 1 over a plus 1 over b. But this one's a little more difficult to deal with. When we have b is greater than or equal to a plus 1, we have b isolated over here, which is nice because we know how to deal with this. This inequality is a lot more weird and difficult to deal with. So it would be better for us if we started by isolating b on that inequality so that we can use it to compare to this one. So let's isolate b. We can start by subtracting 1 over a on both sides, which gives 1 minus 1 over a is greater than or equal to 1 over b. And then we just take the reciprocal on both sides. When we take the reciprocal, we have to flip the inequality sign. So we get 1 over 1 minus 1 over a is less than or equal to 1 over 1 over b is just b. And then to make this more similar to what we have over here, we can write it as b is greater than or equal to 1 over 1 minus 1 over a. So these are the two inequalities we have. And remember, we're looking for the smallest possible value of b. So we have these two inequalities. But when we have two inequalities at the same time, it's a lot more difficult to deal with than when we only have one inequality. So we need to think about how we can deal with this. We can't just set b equal to a plus 1 or b equal to 1 over 1 minus 1 over a, because we know it has to satisfy both of these inequalities. So when I see these two at once, what I'm thinking is we should try to make a graph of these inequalities so that we can visualize better what is the smallest possible value of b. So let's make a graph over here. On the horizontal axis, we'll put a, and on the vertical axis, we'll put b. Now we know that a and b both have to be greater than 1. So we'll put 1 here and here, and we know that a and b have to be in this area right here. First we have b is greater than or equal to a plus 1. That means at a equals 1, b is going to be 1 plus 1, which is 2, right here. And then this line is just going to go straight up like that. And then the other equation, b is greater than or equal to 1 over 1 minus 1 over a. To make this easier to deal with, because we have a complex fraction here, let's multiply by a on the top and bottom to get rid of that. And that'll give us b is greater than or equal to a over a minus 1. So in this case, we know a has to be greater than 1. So let's think about what happens as a approaches 1. Because when a equals 1, we actually get dividing by 0. So that means we're going to have a vertical asymptote at 1. The question is, does b go up or does b go down? So if we think about a being really close to 1, a number slightly greater than 1. On the numerator, we're going to get some number slightly greater than 1. On the denominator, when we take that number and subtract 1, we're going to get a really, really small positive number. So we have about 1 divided by a really small positive number, which means this is actually going to go up towards infinity. So the graph is going to go like this, and then when we go the other way, as a gets bigger and bigger and bigger, what's going to happen is this minus 1 won't really matter that much, and what we're just going to end up with is b is about a over a, which is just 1. So the bigger a gets this way, the closer b is going to get to just 1. So the graph is going to go out like this. And since we need both of these inequalities to be satisfied, we know that we have to be greater than both of these curves. We have to be above both of these curves, which means that the range we're looking at is this range right here. And we're asking, what is the smallest possible value of b? Well, b is this vertical variable, so the smallest possible value is going to be right here at the intersection of the two curves, because we know this is greater than or equal to, so we can be exactly equal to, which means that at the smallest possible value of b, both of these equations are true. b equals a plus 1 and b equals a over a minus 1, because we're on both curves at the same time. But if these equations are both true, and they're both b on this side, then that means a plus 1 has to equal a over a minus 1. And we can use that information to solve for b in the end. So I'm going to clear this board and we can work with those equations. Okay, so we have our two equations here now, and again you can see that because b equals a plus 1 and it also equals a over a minus 1, we know that a plus 1 must equal a over a minus 1. Now we just need to solve for a. So to start, we can multiply by a minus 1 on both sides. If we do a plus 1 times a minus 1, that's the difference of squares, so that gives us a squared minus 1 is equal to a. So we can subtract a, we get a squared minus a minus 1 equals 0. And now we can just use the quadratic formula. So you get a is equal to, b is negative 1, so we get positive 1, plus or minus the square root of b squared is 1, and then minus 4 times a is 1, and then c is negative 1. Divide by 2 times 1 here. So this gives us a is equal to 1 plus or minus the square root of negative times a negative is positive, so this is 1 plus 4, which is 5, over 2. Now we have two answers here, but let's think about what happens if we plug in 1 minus the square root of 5. Well, the square root of 5 is much greater than 1, so if we do 1 minus the square root of 5, what we're going to get is a negative number. But we know a has to be greater than 1, which means that we don't have to worry about this minus. Our a is going to have to be 1 plus the square root of 5 over 2. And now that we have this, all we need to do is plug this into one of our equations and solve for b. This one's a little complicated to deal with, but we can easily use this. We get b equals a plus 1, so that means b is equal to 1 plus the square root of 5 over 2 plus 1. Since 1 is 2 divided by 2, we can write this as 2 plus 1 is 3 plus the square root of 5, and then all divided by 2. That is the smallest possible value of b, and that is our answer.